Let's try that again. Hey everybody, I wanted to go over this assignment, and usually we do this in class and it's really fun. You take a dollar bill and you hold it halfway, you put it halfway through your fingers like this. So you take half of the dollar bill, say pretend this is a dollar bill, and you take about half of it and you put it in between someone's fingers, and then you let go and they try to catch it. Most of the time, that distance, if you calculate how long does it take that distance to fall, it will, it's too long. Our reaction time, the time it takes for our eyes to see it and our brain to react and to close our fingers, it takes 0.14 seconds. Well, if you calculate that distance of a dollar bill for that much to fall, then it's greater than 0.14 seconds, or it's less than 14 seconds, sorry. It's probably less than, so that we don't have enough time to catch it, basically. So this little experiment here is about calculating your reaction time with a ruler. So you need a partner for this. So you might ask a parent or a sibling to just hold a ruler. Make sure you start from 0, and you hold the ruler and they let go, and you catch it. You can't do it yourself because you know when you're gonna let go, right? But if I didn't know, I'd have to react. So we're calculating reaction time. So get someone else to hold it for you. Hold it over your fingers like that. Let go, and see how long it takes. So I got like 17 centimeters. Make sure you're using centimeters. So let's say I got like 17 there, 17 centimeters. Let's take let's say I got 19, and then I got 18. So if you take the average of that, you're going to get 18 centimeters. So then you average it out. You have to add them up, divide by 3. I picked those numbers because I know it's going to average out to 18. So that's centimeters. So to get into meters, you just divide it by 100. So 18 centimeters divided by 100. And so that's going to give me 0.18 meters. Compute your reaction time. Okay, so to do C, we're going to use this. I hate when that happens. We're going to take this equation and we're going to solve for T. So I multiply the 2, divide by G, take the square root. So time is equal to 2D over G square root. So this is the formula you want. So you put in this this 0.18 into the distance. So my distance would be 0.18 meters, and my gravity is always negative 9.8. Plug them into this calculator, and you should get your time, which is what they want for this one. So show your work. You can do this on Whiteboard Fox. Import your picture over. I think that's it for that one. So that's just calculating reaction time. Remember, you can look up reaction times. It's like 0.14 seconds. All right, let's look at what's next. Conceptual questions. A pitcher on a baseball team throws a high lob across home plate. For each part of this event, is the ball in free fall? So free fall, so for an object to be in free fall, the only thing that could be acting on it is gravity. That's the only force. Let's call that the force of gravity. So gravity is the only thing. If this is in someone's hand, or if someone is hitting it with like a baseball bat, ooh, I hate that. So if someone's hitting this with like a baseball bat and putting a force on it, That's not a free fall, right? So is A in free fall? The outfielder is winding up to throw the ball. So someone's going to throw it. The ball is in their hand, and they're going to throw it. The ball is in someone's hand, so that's a no. So I'm going to say A is no. What about B? Oops. So you guys do the rest. The bat is connecting with the ball. I just gave you that one too. No. So you guys do B and C. Oh, I hope I'm recording. Yeah, yeah. Well, am I? I think so. Yeah. All right. So that's a no. All right. Number 2, acceleration due to gravity on the moon is about 1/6 that of the Earth. Compared to on Earth, a ball thrown upwards on the moon will take blank time to return to the surface. So you have to choose A, B, C, or D. So what formula would we use for that? Let's look at time. They're asking for time. How long would it take for something to, the more gravity, there's like an inverse relationship here, right? So the larger the gravity, the shorter the time. That makes sense, right? The less gravity, if you have a small number down here, your time will get larger. So think about that and choose one. And think about when people jump on the moon, how does it look? Are they falling faster? Does it take more time or less time? So I'll let you guys answer that. A student tosses a ball upwards with a velocity of 20 meters per second. Circle the correct answer below. So we have as the ball rises, let me include all this. So what we have here is we have a ball going up and then it's coming down. And so it says as it's rising, I'll do the first one. As the ball rises, its velocity is positive and acceleration is positive. Okay, so we know on our chart, up is positive, to the right is positive. So as the ball rises, its velocity is positive. That sounds right because it's going up. So velocity is positive. It's slowing down. So that means acceleration is negative. And here's a hint. Acceleration is always negative. Gravity is always pulling it down. So as it's going up, it slows. And as it's coming down, it gets faster going down. So velocity will be negative going down. Right? Because velocity depends on what direction it's moving. So as the ball rises, its velocity is positive and acceleration is negative. So that was circling there. So you might want to draw that on there and try to figure it out. Next, let's see. I'll give you, so these are just like the ones we did, the we do, you do, and I went through the process for that. It's the same concept. The physics student stands on the rim of a canyon. So you got someone standing on a canyon. So here's a student, and they want to know how deep is the canyon. They want to know what is this distance from here all the way down to there. All right, how far did it? So they're dropping. I should make it bigger. Let's see. So he's standing on this. That's where they don't know. So this guy is standing on a big thing right there. And we want to know how deep is it? How deep is that canyon? Well, we know time, we know gravity. So the distance is 1/2 g t squared. So this is just like the other problems. Do the guess method, right, and get what d is. Raindrop is falling. When they give us the distance, how long would it take to fall? So this one again is that time equation. 2d over g. And then b, so I'll let you guys copy that for a second. So pause it here and copy those down. Let's look at b. If there were no air resistance, how fast would the raindrop be going? So this is your velocity. Initial velocity is going to be 0. So we need to know, we're going to use the time from A, right? We got t equals on that one. So then you're going to plug in that time, whatever you get, into that. Initial velocity is 0. So it's just gravity times time. How long did that raindrop fall? So you're going to use the time from A and plug it in. Here's the potato gun one. So you fire a potato in the air. It's talking about the maximum height. Let's call it D. We want to know, what is D? And we want to know on A, how long does it take to reach maximum height? Well, we know the final velocity is 0. We know that the potato gun that does not look like a potato gun. Well, anyway, so they fire that potato gun, and we know the initial velocity is 28 meters per second. And we just need the formula for time. So we're going to use this one. But we're going to solve for t. I don't know why the annotate does that. Fi over g. So you're going to get time, and then you'll get distance. So this is first. And then part 2, you get distance, or b. How high does it rise? You use that time you just got, plug it in here. So they all depend on each other. So I would take some notes on this, some paper, or write it down or something, and try to finish it. You can use Whiteboard Fox. Pause it. All right, the last one I would use. This is going to be the same for the whole thing. Let's see. So this negative 9.8, it's going to be the same all the way through. But velocity and x are going to be different. And it says you can use the calculators on 116 and 117. You can do that. That's fine. It's going to look like, so we got velocity, initial velocity of 49, and we're just going to change the time. So let's do a couple of velocities. So you're going to go to page 116. I'll put some links up. Here's page 116, and you can use this calculator. And see, here it says solve for velocity. So acceleration, we're going to change that to negative 9.8. And initial velocity, I think that we said it was 49. Yeah, 49. Oops. So negative 9.8 and initial velocity of 49. So at time equals 0, what do we get? 49. Okay, good. And then what's the next one? At 1 second, we have 39.2. Gotta make sure that's correct. So this is going to be 39.2. Makes sense. How about at time 2? Now I got 29.4. Right? Last one. At time 3, I got 19.6. Okay, so that's velocity. Now, the next page has a calculator for distance. So that's, come on. Oh, there it is. Initial position is 0. Initial velocity is 49. Acceleration is gravity of negative 9.8. So now at 1, we got 44.10. I believe that's here, 44.10. What about time equals 2? And it changes the other time for you. And I got 78.4. And then what about time equals 3? $102.9. All right, so you can keep on going with that. Then we're going to graph. Remember, X is position. And I hate when that happens. And V is velocity. And 9.8 is going to be the same all the way through. So let's get position versus time. So it starts off at 0, 0. Next one at 1, time equals 1. I got 44.1. I'm going to say that's around there somewhere, just estimate. And the next one, at time equals 2, we're at 78. That's close to 80. So that's going to go right there. Time equals 3, I'm at 102.9. That's close to 100. All right, so you can see a pattern there. Connect the dots. So I'm going to let you guys finish that. And then same thing for velocity. Let's move this thing. Can't see it. So velocity, it starts off at 49. So it starts off close to 50. So it might be best to do this on a whiteboard Fox. And then the next one is 39.2. That's close to 40. Next one is 78. No, I'm sorry, 29.4. That's close to 30. And then the last one I have is 19.6. That's close to 20. And so you can see a trend that way. Yeah. So yeah, so that's how you graph these. What I would do, maybe you might have to copy this. Yeah, I guess you'd have to like add a picture, but you have to save it. Perhaps, like I'll show that during class how to do that. But that's it. Hope this wasn't too long. Let's see.